indefinite integrals. All right, this light is kind of flashing, so I'm going to turn that off. Can everybody still see the board okay? Okay, great. Okay, so an indefinite integral might be something like the following example. The integral of x squared dx. So just a few reminders that the dx and the stretched out s, the stretched out s is the integral sign, the dx at the end is representing that infinitesimal idea. Okay? And so these two pieces of information tell us something physically meaningful, but they also tell us an action. They say, in order to evaluate this indefinite integral, what we want to do is find the antiderivative of the thing in the middle, or the integrand. And so our antiderivatives, the way that we calculate this is to add 1 to the power and then divide by the new power or multiply by the reciprocal, either way. So we add 1 to the power, divide by that new power, and then we also need to tack on a plus c at the end. Anybody know why we tack on that plus c?
Because there could be a constant that you don't know about that will become 0 when you put the derivative of it eventually.
Yeah, so if I look at 1/3 x cubed plus c and I take its derivative, well, the derivative of any constant is 0. So I don't know if there was a constant on the function whose derivative is x squared. So I have to throw that plus c on to say, maybe there was a constant, maybe that constant was 0, but maybe it was 352.5. I don't know. Yes?
And isn't it true that because x squared is a function, of course, we haven't defined any starting or ending points, so if you want to know what the area is, which, of course, that just says what's the area of that. It says I don't know what the area is because you didn't tell me where to start or finish, right?
So that's actually a meaningful difference between our indefinite versus our definite integral. Our indefinite integral, without boundaries on this, it unfortunately doesn't really represent an area at all. It really is just saying, use these two values and find the function whose derivative is x squared. And so although the integral sign is used for our definite integrals, the indefinite integrals really can't give us anything about area. But in fact, what it does do is that it tells us, okay, fine. So first of all, find the antiderivative of x squared. And the thing to notice is that an indefinite integral, the final answer will always be some kind of a function, some kind of a value that depends on the variable x, or if it's a dt on the variable t, or if it's ds on the variable s. So it's always a function that depends on the variable attached to the d. Okay, so we also have definite integrals. So definite integrals, an example of a definite integral might be the integral of x squared dx, starting at 1 and ending at 2. So now we have boundaries on our integral. And now the meaning of this changes. The second that we put the boundaries on there, now we're talking about, at least one interpretation is we're talking about area. And so when I look at x squared, and I graph the function y equals x squared, my boundaries tell me that I'm starting at x is equal to 1 and ending at x is equal to 2, and I'm finding the area under my function y equals x squared, below y equals x squared, and above the x-axis. Now if my function dips below the x-axis, then we're talking about a negative value, and we end up in the calculation subtracting off the area that's below the x-axis. So this integral represents the area under y equals x squared and above the x-axis between x equal to 1 and x equal to 2. And so when I'm looking at this, if I want to evaluate this integral, the integral from 1 to 2 of x squared dx, then the fundamental theorem of calculus, part 2, tells us how do I evaluate this integral? Well, first thing I do is find the antiderivative of this function in the middle. So I add 1 to the power, and I divide by that new power. I can throw on the plus c, but with the definite integrals, that plus c is going to end up canceling, so I don't have to worry about it with the definite integrals. But now I want to evaluate this, 1/3 x cubed, between 1 and 2. And so I'll plug in the 2, the top boundary, and then subtract off, plugging in the 1. So in the end, I've got 8/3 minus 1/3, and so I get a final value of 7/3. And so that number right there is a number that's telling me that this shaded region here is 7/3 square units. Okay? And so when I talk about a definite integral, when my values on my boundaries are numbers, then my final answer is going to be a numeric value. It's always going to be a number. So indefinite integrals, our final answer is a function. And with a definite integral, our final answer is most likely going to be a number, unless there's some other random symbols in there. But as long as our boundaries are numbers and there's no weird extra symbols in here, then your final answer will be a number as well. Okay, are there any questions about those? Okay. Well, if I were sitting down there, I might have a question at this point, and my question would be, gosh, what should I be expected to know coming into this course, and what are we going to learn in this course? So a big question is, what indefinite integrals should you know, or should you be expected to know, if not now, then by the end of the week? So what indefinite integrals should we know or be able to calculate? By the end of this week. All right, so to answer that question, I have a job for you. So what I have up here are very, very tiny slips of paper. And on each slip of paper, you will either see an integral, or you'll see some function with a plus c on it. So, for example, one slip of paper might be the integral of x squared dx, and another slip of paper might have 1/3 x cubed plus c. And so your job will be to come up here, grab a slip of paper, and find the person that matches with you. So if you have the integral of x squared dx, you've got to find the person who has 1/3 x cubed plus c. And if you have 1/3 x cubed plus c, you've got to find the person who has the integral, whose integrand is the derivative of 1/3 x cubed. So you want to be able to match these up. Okay? So I encourage you to look at it first and think to yourself, okay, do I know what I'm missing? Do I know what the part is that I'm missing? And if you don't, find somebody in the classroom who can help you. Okay, so I'm going to put these out on the table. Please come up, grab one slip of paper, find the person